So we essentially had these questions and answers that someone posted on LinkedIn. They're around data science, and we want to turn them, make them relevant to brainwaves epilepsy. So slideshow, yeah, we have question 1. Yes, was contributed on LinkedIn by Ivan Reznikov. So go over the questions. We popped it into Gemini. So first of all, it seemed to be obviously able to answer all these questions 100%. Second, we asked, we had a prompt for this document. So essentially we're repeating each question and summarizing it, answering each question, providing the logic of the answer, explaining it to a layperson as well, importantly, so no terminology or as little terminology as possible. And then we give an example from biomedical data, specifically brainwave recordings in epilepsy patients. So how would you use this concept, for example, in this case, cross-validation, in detecting epilepsy seizures in brainwaves in EEG recordings from, well, epilepsy patients. And we gave it so we used Gemini 2.5 Pro for generating a response for this, going over the PDF. This PDF, there's quite a few questions, and now we gave it to NotebookLM. So just let it chat. If you have any questions, pop them in the chat, and I'll intervene. Or if it said something weird, which hopefully no. Gemini is now a BioniChaos CEO, so it better, stay on topic at least.
Have you ever felt just swamped by all the technical jargon in data science? Or maybe wished for a faster way to, really get those complex ideas?
Well, you're in the right place today. We're taking a deep dive into some pretty fundamental data science concepts. Our source material is this really interesting set of data science mock test solutions, specifically focused on EEG applications. So this means we're not just looking at what these concepts are, but we're digging into the how and the why they're so critical, especially for real-world stuff like biomedical applications. We'll focus on how these ideas help us understand brain signals and even detect conditions like epilepsy.
Exactly. And the goal here really is to make these concepts feel immediately relevant. We want to highlight their practical impact, turning what might seem complex into clear insights for you.
Absolutely. Get ready for, hopefully, a few aha moments as we demystify these terms and show you their surprising real-world power. Okay, so let's start with building and training models. A term that always comes up is cross-validation. What's that really all about? Why is it so foundational? Right, cross-validation. It's a crucial technique. Its main job is to give you a realistic assessment of how well your model performs. And, maybe even more importantly, it helps reduce something called overfitting. The basic idea is you split your data set into multiple parts, they're often called folds. Then you repeatedly train the model on, say, most of the folds and test it on the one fold you left out. You keep doing this until every fold has been the test set once. This whole process gives you a much more reliable estimate of how the model will do on new data it hasn't encountered before.
So it's not just about getting a high score on the data you already have. It's about trust, right? Like, can you actually trust this model when it sees something new? Especially in medicine, you can't have a model that looks great on old patient data, but then completely misses something on a new patient. That's dangerous. It's like preparing a student for a big exam. You don't just give them one practice test they might memorize, right? You give them several different ones. That way, they really understand the material, not just the answers to that one test.
That's a perfect analogy, and applying it to the EEG example. Imagine building a model to spot seizures in brainwave recordings. You'd use cross-validation. Maybe split your EEG dataset into, let's say, 10 folds. You train the model on 9 of those folds, test it on the 10th. Repeat that 10 times, rotating which fold is the test set. Averaging the results from those 10 tests gives you a really solid measure of how accurately your model identifies seizures in new patient data. It stops the model from just specializing on the few patients in the initial training set.
Okay, so that prevents over-specializing. But what is that exactly? What happens when a model learns too well from its training data? You mentioned overfitting.
Yes, overfitting. That's exactly the problem. Cross-validation helps fight. Overfitting is when you see a big gap between how well the model performs on the data it was trained on versus how it performs on new, unseen data. Like maybe it gets 95% accuracy on the training set, seems amazing. But then you give it some new test data and the accuracy plummets to, say, 70%. That's a classic sign of overfitting. It means the model didn't really learn the underlying patterns, it just memorized the training examples, including all the noise and random quirks in that specific data, so it can't generalize.
Right. Like the student analogy again. They memorized the practice exam perfectly, got an A plus WAR, but then the real exam had slightly different questions, and they tanked because they didn't actually learn the concepts. And in the medical world, if your seizure detector gets 95% on patient group A during training, but only 70% on new patient group B, that model basically just memorized the specific seizure patterns of group A. It didn't learn what seizures look like in general. That's overfitting.
Precisely. It failed to generalize, which is critical.
So how do we fix that? How do we actively prevent this over-memorization during training? There's a technique for that, right? Regularization.
That's exactly it. Regularization is a technique, or rather a set of techniques, designed specifically to combat overfitting. What it does, essentially, is add a penalty term to the model's learning process. This penalty discourages the model from assigning excessively large weights or parameters. It effectively forces the model to be simpler, to find more general patterns instead of fitting every little wiggle in the training data.
So it's like built-in discipline for the model. It tells it, hey, don't get too complex, focus on the big picture. Like telling that student, okay, you get points for the right answer, but you lose points for every overly complicated step you take. It pushes them towards the simplest, most general solution.
That's a really good way to think about it. When you're dealing with something like EEG data, which can have tons of features, high-dimensional data, it's super easy for a model to overfit. Regularization adds that penalty for large weights, pushing the model to rely on a broader set of features, each with maybe moderate importance, rather than just a few features with huge weights. This leads to better generalization on new patients.
Okay, shifting gears slightly, let's talk about the model setup. What are the things we actually set before training starts versus the things we measure after?
Right. The things you set before training are called hyperparameters. Think of them as the tuning knobs for the learning algorithm itself. For instance, with a random forest model, hyperparameters would be things like estimators how many decision trees you want in the forest, or max depth how deep each tree is allowed to grow. You decide these before you hit train. Things like training accuracy, on the other hand, are performance metrics. They're results you measure after the model has been trained to see how well it did. Accuracy is an outcome, not a setting you choose beforehand.
Okay, got it. So like baking that cake again, hyperparameters are the recipe choices. Oven temp, baking time, how much sugar, you set those first. Training accuracy is like tasting the cake after it's baked to see how good it is. You can't just set the tastiness level in the recipe.
Exactly. So building our random forest for EEG classification, you might set the hyperparameters to use, say, 100 trees, each with a max depth of 20. After training, you might find the training accuracy is 99%. That 99% is a result, a metric, not one of the initial knobs you turned.
Makes sense. So once we've set those knobs, those hyperparameters, how does the model actually learn? How does it adjust itself to get better? There's a learning rate, right?
Yes, the learning rate is key, especially in optimization algorithms like gradient descent, which many models use under the hood. The learning rate is another one of those hyperparameters. It controls how big of a step the model takes each time it adjusts its internal parameters to try and reduce its errors.
Okay, I think I need another analogy here.
Imagine you're blindfolded on a hillside, and your goal is to get to the lowest point, the bottom of the valley. You can feel the slope beneath your feet. You take steps downhill. The learning rate is the size of each step you take. Tiny steps mean you're cautious, you probably won't miss the bottom, but it'll take forever. Huge steps mean you get down faster, but you might completely overshoot the lowest point and end up halfway up the other side. Finding the right step size, the right learning rate, is crucial.
That paints a really clear picture. So for a neural network detecting seizures, the learning rate controls how much it changes its internal settings after seeing a batch of EEG data. Too high, it might never settle on a good solution. Too low, it might take ages to train.
Precisely. It governs the speed and stability of the learning process.
You mentioned internal parameters that the model adjusts. What exactly are those in something like a neural network?
Good question. In a neural network, the parameters are essentially the connection strengths between neurons, these are called weights, and the activation thresholds for neurons, these are called biases. Think of them as all the little internal knobs and dials that the network tunes during learning to transform the input data into the desired output prediction.
That sounds like potentially a lot of knobs and dials. Can you give us a sense of scale, like for a reasonably complex network?
Oh, it can get massive very quickly. Let's take a fairly standard, not even huge, network architecture, maybe something like 784, 128, 64, 10. That means 784 input features, 2 hidden layers with 128 and 64 neurons respectively, and 10 output neurons. Just calculating the weights and biases between layers. Input to first hidden, 784 inputs, 128 neurons, plus 128 biases equals 256 parameters. Second hidden output, 64 inputs, 10 neurons, plus 10 biases equals 650 parameters. Add those up. You're looking at 100,480 plus 8,256 plus 650 equals 109,386 parameters, over 100,000 tunable knobs.
Wow. Okay, that's a lot. So if you feed a chunk of EEG data, maybe represented by 784 data points, into that network, it's adjusting over 100,000 parameters to learn how to tell if that chunk represents a seizure or not. That's incredible.
It really is. It highlights the complexity these models can capture.
So with all these connections and weights, what actually decides if an individual neuron in that network should, like, pass on a signal? What's the trigger?
That's the job of the activation function. Each neuron applies an activation function to its weighted input to determine its output signal. Historically, functions like sigmoid or tan were common. They output values between 0 and 1, or midway 1 and 1, respectively. But these days, especially in the hidden layers of deep networks, the go-to activation function is ReLU, the rectified linear unit.
ReLU. Okay, what makes that one so special?
It's surprisingly simple. The function is just fx equals max 0x. So if the input x is negative, the output is 0. If the input is positive, the output is just x itself. This simplicity makes it computationally very fast. And, crucially, it helps mitigate a problem called the vanishing gradient, which used to make training very deep networks difficult. ReLU keeps the signal flowing better.
So it's basically like an on-off switch, but a bit smarter. Negative input means off, output 0. Positive input means on, and pass the signal through unchanged.
That's a great way to conceptualize it.
And for our EEG seizure detector, using ReLU in the hidden layers helps the network quickly pass along potentially important positive signals that might indicate seizure activity while just shutting down negative or irrelevant inputs. Efficient.
Precisely. It contributes significantly to the effectiveness of modern deep learning.
Okay, let's talk about the data itself for a moment. What happens when our data gets really, really complex? Like too many features or measurements for each sample?
That brings us to the infamous Curse of Dimensionality. It's a term that covers several problems that pop up when you're working with very high dimensional data. The main issue is that as you add more dimensions, your data points become increasingly sparse. They spread out exponentially. With a fixed number of data points, the average distance between them grows rapidly as dimensions increase. This makes it incredibly hard for algorithms to find meaningful patterns or clusters because everything looks far away from everything else.
Right, I think I can picture that. Like if you have 10 dots scattered on a 1-meter line, they might seem somewhat close. But put those same 10 dots inside a 1 by 1 meter square, they're instantly much farther apart on average. Then put them in a 1 by 1 by 1 meter cube. They become really isolated points floating in a vast space, harder to see any structure.
That's a perfect visualization. Now imagine EEG data. You might have, say, 256 electrodes on the scalp. And from each electrode, you extract maybe 10 different frequency band features. That's 256 times 10, 2,560 dimensions. If you only have recordings of a few hundred seizures, your seizure data points are incredibly sparse in that 2,560 dimensional space. It becomes really challenging for a model to learn what a typical seizure looks like because every example seems unique and isolated.
Okay, so that's the curse. If we have too many dimensions making our data sparse and patterns hard to find, how do we fix it? How can we simplify the data but keep the important stuff?
That's precisely where principal component analysis, or PCA, shines. PCA is a dimensionality reduction technique. Its goal is to transform your original set of potentially correlated variables into a new set of uncorrelated variables, called principal components. These components are ordered so that the first few capture most of the variance, or spread, in the original data.
So going back to that stretched oval cloud of data points, PCA finds the longest axis through that cloud. That's the first principal component. It captures the direction of most variation. Then it finds the next longest axis, perpendicular to the first, and so on. You can often describe most of the data's structure using just the first few principal components, effectively reducing the number of dimensions you need to worry about.
Exactly. With high-dimensional EEG data from, say, 128 channels, the signals are often highly correlated. PCA can create new virtual channels, the principal components, which are combinations of the original channels. These components capture the dominant patterns of brain activity across the scalp. Often you can use just the first, say, 10 or 20 principal components as features for your seizure detection model. This drastically simplifies the problem, reducing dimensionality from 128 down to 10 or 20, while hopefully retaining most of the information critical for distinguishing seizures.
That makes sense. Related to having lots of features, can some features actually be redundant, like telling the model the same thing twice?
Yes, absolutely. That issue is called multicollinearity. It happens when two or more of your input features are highly linearly related, meaning they have a strong correlation. For example, if two features have a correlation coefficient of, say, 0.95, it means that when one feature's value goes up, the other feature's value almost always goes up by a predictable amount. They carry very similar information. This redundancy can make your predictive model unstable. The model might struggle to decide which of the two correlated features is truly important, leading to unreliable coefficient estimates and difficulty interpreting the model.
Like trying to predict, I don't know, a child's weight using both their height in feet and their height in meters. They're perfectly correlated, basically redundant information. Adding both doesn't help much and might just confuse things.
That's a perfect example. In an EEG context, imagine two electrodes placed very close together on the scalp. The electrical signals they pick up, and thus any features derived from them, like power in a certain frequency band, are likely to be extremely highly correlated. That's multicollinearity. In practice, you'd likely want to address this, maybe by removing one of the features or perhaps combining them into a single feature to build a more stable and interpretable model.
Okay, let's shift to how models make actual decisions or predictions. For something like logistic regression, it outputs a probability, right? A number between 0 and 1. How does that become a clear yes or no?
Right. Logistic regression gives you that probability. To turn it into a definite classification, a yes, class 1, or no, class 0, you need to apply a decision threshold. The most common default threshold is 0.5. So if the model outputs a probability of 0.5 or greater, you classify the instance as 1. If the probability is less than 0.5, you classify it as 0. Simple enough. So if the model spits out probabilities like 0.8, 0.3, 0.9, 0.1, using that 0.5 threshold turns it into 1010. It's like the weather forecast giving the chance of rain as a decimal. Your threshold is your personal decision point. Maybe you say, if it's 0.5 or higher, I'm taking my umbrella, that's class 1. If it's lower, I'll risk it, class 0.
That's a great way to put it. And the threshold itself can sometimes be adjusted depending on the specific problem and whether you care more about avoiding false positives or false negatives. But applying it to our EEG example, imagine an AI analyzing 1-second EEG segments. For 4 consecutive seconds, it outputs seizure probabilities, 0.8, 0.3, 0.9, 0.1. With a 0.5 threshold, a real-time monitoring system would flag the first and third seconds as potential seizure, 1, and the second and fourth as normal.
0. Makes sense. Now, logistic regression implies a kind of linear boundary, but what if the data isn't so easily separated? What if the yes cases and no cases are all mixed up in a complex way? That's a common scenario, and it's where support vector machines, or SVMs, really show their power, particularly with nonlinear kernels. A standard SVM with a linear kernel tries to find the best straight line, or flat plane, in higher dimensions to separate the classes. If your data points are tangled up in a way that no single line can cleanly divide them, the data is called non-linearly separable, and a linear SVM will perform poorly. The solution is to use a nonlinear kernel. Popular choices include the radial basis function, RBF kernel, or polynomial kernels. What these kernels cleverly do is implicitly map your data into a much higher dimensional space. The magic is that in this higher dimensional space, the classes might become linearly separable. So the SVM can then find a simple flat plane separator in that higher dimension, which corresponds to a complex nonlinear boundary back in your original feature space.
Whoa, okay. So imagine you have red and blue dots scattered on a dinner plate, totally mixed up. You can't draw one straight line to separate them. A nonlinear kernel is like, you hit the bottom of the plate really hard, the red dots fly up into the air, while the blue dots stay on the plate. Now, in this 3D space, plate surface plus height, it's easy. You can just slide a flat piece of cardboard horizontally between the blue dots on the plate and the red dots hovering above. That flat cardboard is your simple linear separator in 3D, but it corresponds to a complex boundary back on the 2D plate.
That is a fantastic analogy. It captures the essence perfectly. So if you're using an SVM to distinguish between, say, two different complex types of epileptic seizures based on EEG features, the decision boundary is probably not going to be a simple line. If your linear SVM isn't working well, trying a RBF kernel is usually the next logical step. It allows the SVM to learn that complex, wiggly boundary needed to separate the seizure types effectively.
Cool. Let's quickly revisit cross-validation. We talked about K-folds. Can you just spell out what that means in terms of the percentages used for training versus testing, like for 5-fold?
Sure thing. In K-fold cross-validation, you divide your data into K equal-sized chunks or folds. If you choose K5, you split the data into 5 folds. Each fold represents 15th or 20% of your data. In each round or iteration of the cross-validation, you use one of those folds, 20% of the data, as your test set, and you use the remaining K1 folds, in this case, 4 folds, which is 40 fixed or 80% of the data, as your training set. You repeat this process 5 times, making sure each fold gets its turn to be the test set.
Okay, crystal clear. So 5-fold always means an 80% training, 20% testing split in each iteration, like using 4 chapters of a 5-chapter book to study and testing yourself on the 5th chapter, then rotating which chapter is the test.
Precisely. If you had 1,000 EEG segments, 5-fold CV means 5 iterations. In each one, you train on 800 segments, 80%, and test on 200 segments, 20%. It's a very standard and robust way to evaluate model performance.
Speaking of performance, let's dive into evaluation metrics. We've trained our model. How do we know if it's actually any good? Let's start with the most basic one, accuracy.
Right. Accuracy is often the first metric people look at. It's defined simply as the proportion of total predictions that were correct. The formula is accuracy, number of true positives plus number of true negatives, total number of predictions. Let's use the example numbers from the source. Suppose a model made predictions and we found true positives, TP, 85, true negatives, TN, 120, false positives, FP, 15 false negatives, FN, 20. So the total number of correct predictions is TP plus TN equals 85 plus 120 equals 205. The total number of predictions made is TP plus TN plus FP plus FN equals about 85 plus 120 plus 15 plus 20 equals 240. Accuracy is then 205 divided by 240, which equals about 0.854. So roughly 85.4% accuracy.
Okay, so out of 240 predictions, they got 205, right? About 85% correct. Seems straightforward.
It is straightforward. So for an EEG model analyzing 240 segments, if it correctly flags 85 as seizures, TP, and correctly identifies 120 as normal, TN, its overall accuracy is 85.4%. It's right about 85% of the time.
But accuracy isn't always the whole story, right? What about models that predict a continuous value, like a quantity or a score, not just a yes-no class?
Exactly. For those regression models, accuracy doesn't really apply. A very common metric is mean squared error, or MSE. MSE calculates the average of the squared differences between the actual values and the predicted values. You square the errors so that larger errors are penalized more heavily, and also so that positive and negative errors don't cancel each other out. The key thing to remember is that lower MSE is better. It means the model's predictions are, on average, closer to the true values.
So if Model A has an MSE of 25 and Model B has an MSE of 16, Model B is the winner.
Correct. Model B is performing better because its average squared error is smaller.
It's like a golf score, then lower is better. And squaring the error really punishes those way-off predictions. If you're predicting house prices, a model with lower MSE is generally making more accurate price estimates.
That's a good analogy. If you were building a model to predict, say, the expected duration of an epileptic seizure in seconds, and Model A had an MSE of 25, meaning the average squared error was 25 seconds squared, while Model B had an MSE of 16, you'd prefer Model B because its duration predictions are more accurate on average.
Is there another error metric for regression that's maybe a bit easier to interpret directly? Squaring things sometimes makes the units weird.
Yes, there is. I mean, absolute error, or MAU. Instead of squaring the differences between actual and predicted values, MAE just takes the absolute value of the differences and then averages them. So it measures the average magnitude of the errors in your predictions, regardless of their direction, over or under prediction. The units of MAE are the same as the units of your target variable, which makes it quite intuitive. Let's use the example. Actual values: 10, 15, 12, 8, 20. Predicted values: 9, 16, 11, 9, 18. The absolute errors are 10, 9, 1, 15, 16, 1. 12, 11, 1, 8, 9, 1, 20, 18, 2. The sum of these absolute errors is 1 plus 1 plus 1 plus 1 plus 2 equals 6. Since there are 5 data points, the MAE is the sum divided by 5. 6, 5 equals 1.2.
Okay. So an MAE of 1.2 literally means that, on average, the model's predictions were off by 1.2 units from the actual value. That is pretty intuitive.
Exactly. If a model predicts seizure severity on a scale of 1 to 25, and it has an MAE of 1.2, that tells clinicians that, on average, the model's severity prediction is likely to be within 1.2 points of the true severity. It gives a direct sense of the typical error margin.
Now, going back to classification metrics like accuracy, what happens if the data is really lopsided? Like you're trying to detect a very rare event, maybe 99% of the data is normal and only 1% is the event. Can accuracy be misleading then?
Oh, absolutely. Accuracy is notoriously misleading on highly imbalanced data sets. Think about it. If only 1% of your data is the positive class, like a rare disease or a seizure event, a lazy model could just predict negative for every single case. That model would achieve 99% accuracy. Sounds great, but it's completely useless because it never finds the rare event you actually care about. In these situations, you need metrics that focus on how well the model identifies the rare class. The F1 score is a much better choice here.
F1 score. Okay, what does that capture?
The F1 score is the harmonic mean of two other metrics, precision and recall. Precision asks, of all the times the model predicted positive, how often was it actually correct? Recall asks, of all the actual positive cases, how many did the model correctly identify? The F1 score combines these. To get a high F1 score, a model needs to have both high precision, not making too many false positive errors, and high recall, not missing too many actual positive cases. It balances the two.
Okay, that makes sense. Like being a detective looking for that one rare clue. Accuracy is bad because saying nothing here 99% of the time looks good but finds nothing. F1 score is better. It measures. Did you find the clue when it was there? Recall. And when you shouted, found it, was it actually the clue? Precision. You need both to be a good detective.
That's a perfect analogy. For EEG seizure detection, seizures are usually the rare positive class. Normal brain activity is the common negative class. A model just predicting normal all the time gets high accuracy, but zero recall, making it useless. The F1 score is preferred because it will only be high if the model successfully identifies most of the true seizures, high recall, without constantly raising false alarms during normal periods, high precision.
All right, let's move into some more advanced techniques. Can AI look at sequences of data, like EEG, over time, and actually predict future events?
Yes, that's the domain of time series forecasting, predicting future values based on past ordered observations. And for complex sequential data, like EEG, a type of neural network called LSTM, long short-term memory, is particularly well suited. LSTMs are a special kind of recurrent neural network, RNN, designed specifically to learn long-range dependencies in sequential data. They have internal memory cells that allow them to remember relevant information from much earlier in the sequence, which is crucial for many time series tasks. Other methods mentioned in the source, like k-means, which is for clustering, standard random forest, which doesn't inherently handle sequences well, or PCA for dimensionality reduction, are not designed for time series forecasting. LSTMs are really the tool for that job.
So predicting the stock market, or tomorrow's weather, those are time series problems. And LSTM acts like a forecaster who doesn't just look at yesterday, but remembers important patterns from last week, last month, maybe even last year to make a better prediction.
Exactly. And a really exciting application in the biomedical field is seizure forecasting from EEG data. The goal isn't just detection, but predicting that a seizure is likely to occur in the near future, maybe minutes in advance. This is fundamentally a time series forecasting problem, analyzing the sequence of EEG patterns over time. LSTM networks are one of the leading approaches being researched for this, trying to learn those subtle, time-dependent precursors to a seizure.
We touched on random forests earlier, which combine multiple models. What's the general idea behind combining models? Are there different strategies?
Right, combining models is called ensemble learning. The core idea is that a committee of models often performs better than any single individual model. There are two main strategies, bagging and boosting. Bagging, which stands for bootstrap aggregating, is what random forests use. The idea is to train many models, like decision trees, independently and in parallel. Each model is trained on a different random subset of the original data, drawn with replacement. The final prediction is typically made by averaging the predictions for regression or taking a majority vote for classification from all the individual models. Boosting, on the other hand, builds the models sequentially. Each new model tries to correct the errors made by the previous models. It focuses on the data points that were previously misclassified, giving them more weight. Examples include AdaBoost and gradient boosting machines, GBM.
Okay, let me try an analogy. Imagine a group of artists drawing a portrait. Bagging is like giving 10 artists slightly different photos of the person, random data subsets, and having them all draw their own portrait simultaneously. Then you digitally average all 10 portraits to get the final image. Boosting is more like one artist starts with a basic sketch. A second artist looks at it, identifies the biggest mistakes, and corrects them. Then a third artist looks at the corrected version, finds its biggest remaining mistakes, and fixes those. They work sequentially, each improving on the last.
That's a really excellent way to differentiate them. Captures the parallel versus sequential nature perfectly. So, in EEG seizure detection, a random forest, bagging, trains hundreds of decision trees concurrently on different bootstrap samples of EEG segments, and the final decision, seizure, or normal, comes from a majority vote. A boosting model might start with a simple classifier, find the EEG segments it got wrong, then train a second classifier focusing specifically on those difficult segments, and continue this process, building a strong final model sequentially.
So what's the big win? Why go through the trouble of building hundreds or thousands of models instead of just one? What's the advantage of these ensemble methods?
The primary advantage, almost universally observed, is better performance. Ensemble models typically achieve higher accuracy, better generalization, and more robustness compared to a single model. It boils down to the wisdom of the crowds. Individual models might have their own biases or make specific errors. By combining many diverse models, their individual errors tend to average out or cancel each other. This leads to a final prediction that is more stable, less prone to overfitting, and generally more accurate on unseen data.
Right. It's like asking one person a really tough trivia question, they might get it wrong. But if you poll 1,000 people and take the most common answer, you're much more likely to be correct. Ensembles apply that logic to AI models.
Precisely. A single decision tree trying to classify EEG might be very sensitive to noise or small variations in the data. But a random forest, an ensemble of hundreds of slightly different trees, is far more robust. An error made by one tree is likely outweighed by the correct votes of the majority, leading to a more reliable clinical tool.
Okay, one last concept, shifting gears a bit again. What if our data isn't nicely structured numbers from sensors, but say text, like doctor's notes or medical reports? How do we find the important information there? There's something called TF-IDF.
Yes, TF-IDF. It stands for Term Frequency, Inverse Document Frequency. It's a fundamental concept in natural language processing, NLP, and information retrieval, used to score the importance of a word within a document that's part of a larger collection or corpus. It has two components: term frequency, TF. This is simple. How often does a specific word appear in a particular document? More occurrences mean higher TF. Inverse document frequency, IDF. This measures how common or rare a word is across the entire collection of documents. Words that appear in many, many documents, like the, is, and, get a very low IDF score. Words that appear in only a few documents get a high IDF score. They are more discriminating.
So the TF-IDF score for a word in a document is high if that word appears frequently in that specific document, high TF-IDF, but is relatively rare across all the other documents, high IDF. Is that right?
Exactly. It finds words that are characteristic of a particular document.
So it helps a computer pinpoint the key terms. Like in a news article about politics, the word election might appear many times, high TF, and might be relatively rare across a huge corpus of general documents, high IDF, giving it a high TF-IDF score for that article. But a word like because would have a low IDF score everywhere.
That's a perfect illustration. And while TF-IDF originated in NLP for text documents, the underlying principle has relevance elsewhere too. Imagine you have thousands of neurologist reports associated with EEG recordings. You want to automatically identify all reports discussing a specific, rare type of seizure syndrome. You could use TF-IDF on the text of these reports. Medical terms specific to that rare syndrome would likely have a high term frequency within the relevant reports and a high inverse document frequency across the entire database of reports, since the syndrome is rare. This high TF-IDF score would make those terms powerful indicators for classifying or retrieving those specific reports.
Wow. Okay, we've really covered a lot of ground there. From the basics of checking model performance with cross-validation, to handling overfitting with regularization, understanding hyperparameters, diving into neural networks with ReLU and parameter counts, then tackling data issues like dimensionality with PCA, making decisions with logistic regression thresholds and SVM kernels, evaluating performance with accuracy, MAC, MAE, and the crucial F1 score for imbalanced data. all the way to advanced methods like LSTMs for forecasting and the power of ensemble methods like bagging and boosting, and even TF-IDF for finding key terms. That's quite a journey through data science concepts.
It really is. And what's truly fascinating, I think, is seeing how these ideas, which can seem quite mathematical or computational on the surface, translate so directly into powerful practical tools. You've seen their potential, especially in a field as critical as medicine, to significantly enhance how we understand complex biological signals like EEG, detect conditions, and maybe even predict them.
Yeah, it gives you real appreciation for the precision involved, the clever workarounds for challenges like the Curse of Dimensionality, and just the sheer ingenuity behind making these algorithms work effectively in the real world.
Which leads to a final thought, perhaps. We've seen how these algorithms can analyze incredibly complex data like EEG to detect current states, like seizures. But given their power to learn intricate patterns, especially sequential ones with things like LSTMs,
But
how might these advancements move beyond just detection? Could they learn to genuinely predict, or maybe even guide interventions to prevent neurological events in ways we're only just starting to scratch the surface of? Something for you to think about.
Yeah, feels like I've been to a very long lecture. That's okay. What's their retention? What do you think the retention is like out of notebook LM summary? Well, we requested it, so it's meant to be relevant. Yeah, it's good that you can just pop this exam sheet, and then just add examples that will be more relevant to you from whatever your field. Should we test our retention straight away? Probably not. I think there's what I heard some supposedly evidence that you shouldn't be, doing a retention test straight after the lecture. So I might do it at another time. We might be actually deploying a lot of these things as interactive web applications. So that will help us understand these concepts even further.
We're making powerful biomedical tools accessible to everyone.
Ever wondered what your brainwaves sound like? Or look like? Ever wanted to play with real scientific tools? Ours are free and open source. You won't believe what you can do with your own data.
Want to dive into data science? Start with our interactive tools.
Go ahead. Play with the data. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
There is a human in the loop, obviously, so if you have any questions, pop them in the chat. I probably won't be able to answer them myself anyway, so I'll have to give them to one of the models available to us. We have Gemini standalone, and we also pretty much have all the other major models through GitHub Copilot. Through GitHub Copilot.